Hi, it's Sir Ellie again. Welcome to General Physics 1. I hope you have your notebooks, your pen, your calculators, and snacks with you. For this video lecture series, we will still be discussing motion in one dimension, but focusing in uniformly accelerated motion using the idea of freely falling bodies. Our objectives for today: translate verbal description of a physical situation involving different quantities in motion, specifically freely falling bodies, solve problems which involve uniformly accelerated motion, specifically freely falling bodies, and appreciate the study of uniformly accelerated motion in different real-life applications. Let's start. Under the uniformly accelerated motion, we have what we call freely falling bodies. For years, people believed that when you have a feather and a bowling ball drop from the top of the building, the bowling ball will reach the ground first. It was the teachings of a great philosopher Aristotle held that more massive objects would fall faster than lighter ones. But it was an Italian astronomer named Galileo Galilei who have presented the concepts that we will be using concerning falling bodies. Galileo argued that a body would fall with a downward acceleration that is constant and independent of its weight. There were experiments done and it proves that Galileo was right. The massive object and the light object would reach the ground at the same time if we were to neglect the air resistance. Regardless of their size and weight, all bodies at specific elevations will fall with the same downward acceleration. On August 2, 1971, an experiment was conducted on the moon by astronaut David Scott. He simultaneously dropped a hammer and a feather, and what happened is that it fell together to the surface of the moon. This experiment can also be conducted here on Earth if the room is a vacuum and air resistance is being neglected, just like what we have here. Regardless of its initial motion, any object that is freely moving under the influence of gravity close to the surface of the Earth can be considered a freely falling body. It may be the object is being thrown upward or downward, and objects released from rest or being dropped. These freely falling bodies experience acceleration directed downwards, regardless of their initial motion. The constant acceleration of a freely falling body is called the acceleration due to gravity. We will be denoting the magnitude of this acceleration as g. We will be using the approximate value of g at or near the surface of the Earth, wherein g is equal to 9.80 meters per second squared. That's why our acceleration here in freely falling bodies, ay, is just equal to the negative of g, or that is negative 9.80 meters per second squared. We now have this one. Suppose you have an egg being thrown upwards. In general, if you throw something upwards, its speed will get less and less as it reaches the maximum height. The object or the egg should be slowing down as it travels up because the velocity vector is pointing upwards, but the acceleration vector is pointing downwards. As it travels down from the maximum height, the object should be speeding up, or it is moving faster and faster. The speed is getting greater compared to its speed at the maximum height as it goes down. At the maximum height, let's have y max, the speed of the object will become 0 or instantaneously 0. It will go down since the acceleration vector is pointing down. Also, do not confuse that just because the velocity or speed is 0, the acceleration at maximum height will also be 0. The acceleration at maximum height will still be equal to the acceleration due to gravity, and it is still pointing downwards. That's why it will always go down. That is why it is under constant acceleration, because at any point, the acceleration will always be the same. Also looking at v1y and v3y and voy and v4y. v1y and v3y, their speeds. Again, their speed, the magnitude of their velocities will just be the same, but the directions are opposite. v1y will be pointing up while v3y is going down. So you can see v1y, it is belonging to the going up motion, while v3y is going down. Same thing with our VOY and V4Y. For example, if v1y will have a positive 10 meters per second, obviously v3y should have a negative 10 meters per second velocity. Also, the acceleration versus time graph of any freely falling body should also show a constant acceleration. Meaning to say, the graph of our acceleration versus time graph is just a horizontal line, wherein the horizontal line is from the negative 9.8 meters per second squared. Freely falling bodies are still under uniformly accelerated motion. But this time, we already know what is the value of our acceleration already, and that is negative 9.8 meters per second squared. Hence, we will still be using the formulas that we have derived from the previous video. But this time, we will be replacing the x, all x's, to y. Take note that our acceleration is always going downwards with the magnitude of the acceleration due to gravity. The equations that we will be using now are the following. You do not have to memorize this one and to memorize the other one. Take note, we did not change our equations. They are just the same equations from before. We just modified it with our understanding that freely falling bodies moving along the vertical or y-axis and the acceleration is pointing downwards with the magnitude of g. So we're ready for an example. We now have example number 1. An avocado fell from the top of the tree for 2 seconds before it hit the ground. A. What is the acceleration of the avocado? B. Calculate for the velocity of the avocado as it reaches the ground. C. How far, looking for the distance, does the avocado fall from the top of the tree? D. What is the acceleration of the avocado as it reaches the ground? Before anything else, it is better for us to illustrate our problem. This is an example of our illustration. As you can see, I have literally drawn an avocado. It is coming from top going down. With my vectors, my acceleration vector ay is just equal to negative g, that is pointing downwards. I am asked for the acceleration. I am asked about the velocity of our avocado as it reached the ground. I am asked for the distance, that is y. And D, what is the acceleration of the avocado as it reaches the ground? We can now answer letter A. There is no need for us to solve for the acceleration of our avocado. Since free fall is under UAM, uniformly accelerated motion, we can have the acceleration of our avocado as negative 9.80 meters per second squared. Let's solve for letter B. Solving for the velocity of the avocado as it reaches the ground. We have assumed that the top of the tree will be the zero initial position. We note that all the motion going down as negative. So we will be expecting a negative velocity since the avocado is falling. We also know that the time it took to reach the ground, t1, and the acceleration is negative g. We will be using this equation, vy is equal to voy plus ayt. So v1y is just equal to voy plus ayt. And now I could substitute everything together, wherein v1y now is just equal to negative 19.60 meters per second. The velocity of the avocado as it reaches the ground is negative 19.60 meters per second. If asked to solve for the speed or to get the speed, the answer would just be the magnitude of our velocity, and that is 19.6 meters per second. Let's have letter C. Solving for the distance from the top of the tree to the ground. We need to know the position y1 first to get the distance. For this, we will be using the equation y is equal to yo plus voyt plus 1 half ayt squared. We now have y1 is equal to yo plus voyt1 plus 1 half ayt1 squared. Substituting all my known variables, I could get y1 now, that is equal to negative 19.60 meters. The position now of the avocado after 2 seconds is negative 19.6 meters. Take note, that is just the position y1. We need to get y. So the avocado traveled a distance of 19.6 meters. Letter D, another simple answer. Since it is really under UAM, the acceleration of the avocado as it hits the ground is still negative of g or negative 9.80 meters per second squared. We now have example number 2. A kid throws his toy downwards from a treehouse with an initial speed of 1 meter per second. The treehouse is 8 meters above the ground. Letter A. Calculate for the velocity of the toy after 1 second. B. How much time will it take for the toy to travel 5 meters? C. At what time will the toy reach the ground? And lastly, letter D. Calculate the speed of the toy as it reaches the ground. It is better for us to illustrate our problem. So we now have this illustration. The illustration to this example shows that at t is equal to 0, the velocity vector VOY is pointing downwards with a magnitude of 1 meter per second. It is because the problem states that the boy throws his toy from a treehouse with an initial speed of 1 meters per second. Throws his toy downwards. Also, at this time, we will set this one as our initial position YO is equal to 0. We can easily solve for letter A. Calculate for the velocity of the toy after 1 second. For this, we will be using this equation. Vy is equal to Voy plus Ayt. We have V1y is equal to Voy plus Ay T2. And substituting everything that we know, we have V1y that is now equal to negative 10.80 meters per second. The velocity of the toy is negative 10.80 meters per second. It is negative since our toy is going down. We now have letter B, calculating for how much time it took for the toy to travel 5 meters down. The position of our toy, y1, is equal to negative 5 meters with respect to yo. To solve for the time it took to go down 5 meters, we will be using the equation y is equal to yo plus voyt plus 1 half ayt squared. We now have this equation. Negative 5 meters is equal to negative 1 meters per second t1, negative 4.90 meters per second squared t1 squared. Rearranging this equation, because this is a quadratic equation, I have only one unknown, and that is my t1. And solving for t1, I will make use of my quadratic equation. And from our mathematics, we already know from our equation where's a, where's b, and where's c, carrying the signs also. So solving for the first value of time, we now have t is equal to 0.9312 seconds. Solving for the second value of time, we now have t prime that is equal to negative 1.117 seconds. We have two values for time. Since there is no negative time, we will neglect t prime. So the answer for the value of t1, it is equal to 0.9312 seconds. In conclusion, it will take 0.9312 seconds for the toy to reach 5 meters. We move on to letter C, solving for how much time it took for our toy to reach the ground. The position of the toy at y3 is just equal to negative 8 meters. We will still be using our equation from the previous one. That is, y is equal to yo plus voyt plus 1 half ayt squared. And we will be analyzing it from point 0 to point 3. That's why we now have y3 is equal to yo plus voy t3 plus 1 half ayt3 squared. Substituting everything that we know, we now have the final equation. That is 4.90 meters per second squared t3 squared plus 1 meter per second t3 minus 8 meters is equal to 0. Solving for the first value of time using the quadratic equation, we can solve the first value that is equal to 1.180 seconds. And we have the second one, that is t prime. We have t prime that is equal to negative 1.384 seconds. We have two values for time, and since there is no negative time, we will neglect t prime. So the answer for the value of t3 is equal to 1.180 seconds. It will take 1.180 seconds for the toy to reach the ground. We are now ready to solve for letter D, calculating for the speed of the toy as it reaches the ground. To find the speed, we will be using this equation. Vy squared is equal to Voy squared plus 2ay times y minus yo. It is also okay to use the different equations using the answers that we have already solved. But it is a good practice for us to use only the given. We already know the acceleration, the initial velocity, and positions, so might as well take advantage of it. That's why we end up with this equation. V3y squared is equal to Voy squared plus 2ay times y3 minus yo. Substituting everything we know, we can actually solve for V3y. V3y is equal to plus minus 12.56 meters per second. It is because the square root will give us two values. We got a positive and a negative value. We will be using the negative value since the toy is going down. So the toy will have a velocity of negative 12.56 meters per second as it reached the ground. Looking back at the question, calculate the speed. We are asked about the speed. So we only need the magnitude of V3y. The speed of the toy now is 12.56 meters per second as it will reach the ground. Now it's your turn to solve. I have here the try it on your own part. You can pause this video and take a screenshot. And here are the illustration for our try it on your own. So yay, this is the end for this video lecture series. We have translated verbal description of a physical situation involving different quantities in motion, specifically freely falling bodies. We have solved problems which involve UAM, specifically freely falling bodies. And lastly, we have appreciated the study of UAM in different real-life applications. This is actually the end for motion in one dimension. Next time, we will be tackling motion in 2 to 3 dimensions. And it will still be very easy for us all. See you in the next video.